Good morning, good afternoon, good evening, everybody, wherever you are. I am Giovanni Losurdo. I am the spokesperson of the Virgo collaboration, and I'm here today to welcome you to the second LIGO Virgo KAGRA webinar. This one is about the event that we have dubbed GW190521, which we have published yesterday. These papers are the outcome of an intense work pursued by the LIGO Scientific Collaboration and the Virgo Collaboration, and we are pleased to present it to the broader scientific community today. The webinar will be moderated by Alan Weinstein, Caltech Professor of Physics, and I'm very pleased to leave the floor. Alan, up to you.
Thank you very much, Giovanni. Welcome, everybody. I hope you can see the first slide. Let me know if you can't. Okay, thanks for attending this webinar. We have over 500 participants. So on behalf of the LIGO Scientific Collaboration and the Virgo Collaboration, we're presenting results on gravitational wave event GW190521, which was observed by LIGO and Virgo in May 21, 2019. It's consistent with being radiated from the merger of a binary black hole system with a total mass of 150 solar masses, making it the most massive binary black hole system observed by LIGO and Virgo to date. We've written two papers on this event, which were published yesterday. You can see them on the first slide. The first one is what we call the discovery paper in Physical Review Letters. The second, much longer one, is on physical and astrophysical implications of this event. It's in Astrophysical Journal Letters. We also have a large and rather comprehensive data release associated with this event, including strain data, parameter estimation samples, figures, etc. Now we will have a presentation by 4 of our team members, followed by a Q&A, and we'll try to get to as many questions as we can at the end. Don't wait to the end to ask your question. Put it in the Q&A chat box right that you should have in front of you if you're in Zoom. People can upvote questions. And then at the end, we'll order our responses according to the number of upvotes a question gets. So put in your question sooner rather than later, and others can upvote it. We have 4 speakers today. Let me introduce them all in one go. We have Brendan O'Brien, who's a graduate student at the University of Florida. We have Tito Dalcantin, who is a CNRS researcher at the IJC lab at Orsay in France. We have Juan Calderon Bustillo, who is a research assistant professor at the Chinese University of Hong Kong. And we have Michela Mappelli, professor of astrophysics at the University of Padova in Italy. We also have experts from LIGO and Virgo on hand to answer questions that might come up that the panelists would defer to the real expert on the subject. Our first speaker today is Brendan. So Brendan, please take it away.
All right, thank you, Alan. You can go ahead and move to slide 2. So before we begin discussing the newest LIGO Virgo discovery, I'd like to take a moment to remind the broader audience what exactly it is that we're measuring. Well, a gravitational wave is a ripple in space-time caused by accelerating masses. Now, these waves travel at the speed of light, and they stretch and squeeze space as they move through it. Now, in general, there are many different source types which could generate gravitational waves, but as we've seen with LIGO Virgo, one of the best sources is colliding black holes and neutron stars. Currently, we have 3 Earth-based detectors in our detector network. That's LIGO Hanford, LIGO Livingston, and Virgo, which is based in Italy. Now, as a reminder, these detectors are not your typical telescope. These are massive instruments which stretch up to a few kilometers long, and they act as antennas to detect incoming gravitational waves. Move to slide 3. Now, the detector network has been operating in its advanced configuration since 2015. And if you look at the timeline to the left, you can see that the 2 LIGO detectors were operational during the first observing run, named 01. The number here of 80 megaparsecs gives how far away we can see a binary neutron star source on average. And it gives a sense of how sensitive our detectors are and how much our sensitivity improves throughout the years. In 02, Virgo joined the detector network, and in 03, we had our longest observing run to date, and our best sensitivity yet. Now we can see a direct consequence of this improved sensitivity in the plot to the right. Here the x-axis shows the number of days in operation, and the y-axis shows the cumulative number of events or candidate events which LIGO Virgo has made public. So you can see that by the end of the second observing run, we had about 10 events. And at the end of the third observing run, we reported on nearly 70 events or event candidates. Moving to slide 4. Now to discuss the discovery which brought us all here today, GW190521. Now this is a unique gravitational wave event in more ways than one, as we'll learn together throughout the hour. As mentioned by Alan, this discovery and its implications are described in 2 papers which are now public. Now, if you look at the bottom panel here, you'll see a 3-panel plot, and what we notice is that the gravitational wave event is present in all 3 detectors. Here, the light blue color represents the detector strain data, and all other colors represent reconstructions of the GW signal by various pipelines. And really, there's 2 main takeaways here. First is that the signal is visible in all detectors. And second, the signal is very short in duration, and we'll discuss the implications of that later in the talk. Now, if we move on to slide 5, we can take a look at the signal through a different lens. Now, in the top panel, we're showing the first gravitational wave detection made back in 2015. That's GW190521. And the plots which I'm showing here are time frequency plots. So you can see the time frequency evolution of the signal. So the x-axis is time, the y-axis is frequency, and the z-axis is depicted by color, gives the energy of the signal. And you'll notice that this signal has an increasing time frequency structure, and we call this the characteristic chirp structure. Now, the dynamics of a binary black hole are described in 3 stages, as pictured in the top right. There's the in-spiral, the merger, and the ring down. And in the in-spiral phase, the 2 component black holes orbit around one another, and their orbital radius begins to shrink as gravitational waves are emitted from the system. And it is in this stage it's this stage which is responsible for the characteristic chirp structure. Now, by contrast, if we take a look at the newest discovery, GW190521 in the bottom panel, although we do see some increase in frequency, it generally lacks the same chirp structure. So the question is, why exactly does this signal not look like a typical LIGO Virgo binary black hole merger? Well, if we move to slide 6, now we can understand why this signal looks so different by looking at how our detectors respond to gravitational waves, specifically from binary black hole mergers. Now, our detectors, as I mentioned, they measure the stretching and squeezing of space-time caused by a passing gravitational wave. Now, the black curve on the left plot shows the sensitivity of one of our detectors as a function of frequency. And so the y-axis here tells us how well our detector measures the stretching and squeezing of space-time. In general, the lower the black curve, the better our sensitivity is. Now, looking again at our first detection, which is shown in blue, we see that all 3 stages, in spiral, merger, and ring down, are detectable. That is, they're above our detector sensitivity. Now, in general, higher mass binaries correspond to lower frequency gravitational wave emission. So if we look at the second most massive LIGO Virgo detection to date, which is shown in orange, we see that it's pushed to the left with respect to GW150914. So it's lower in frequency. And further still to the left, we see our latest detection, GW190521. And here we see that most of the in-spiral for this signal is eaten away by the low-frequency seismic noise of the detector. And this is the reason why the signal morphology of this event is so different from other binary black holes detected by LIGO Virgo. Now we can move to slide 7. So what I've described so far is certainly interesting, but it does not yet distinguish this event as unique astrophysically. And to understand that, we have to look at GW190521 in the context of all other LIGO Virgo detections and really all black hole detections in general. So the plot to the left shows the full mass spectrum of detected neutron stars and black holes. The y-axis here gives the mass of the compact object in solar masses. So if we start from the very bottom of the plot, we see electromagnetic observations of neutron stars, and those are depicted in yellow. In orange, we see binary neutron star systems detected by LIGO Virgo. Now, as we move up the plot, we see the electromagnetic observation of black holes, shown in purple, and binary black hole mergers detected by LIGO Virgo, shown in blue and in green. Here, the blue circles represent the component mass black holes, and the green circles represent the final, or the remnant, mass black hole. So far, LIGO has reported 12 binary black hole mergers. Now, immediately from this plot, it's clear to see that GW190521, which is illuminated here, is the most massive of these binary black hole detections. But really, it's more than that. Along the y-axis, I've divided the mass spectrum into 3 regions. We have the so-called stellar mass graveyard, intermediate mass black holes, and supermassive black holes. And the remnant mass black hole of GW190521 has a mass well above the 100 solar mass cutoff, marking it as an intermediate mass black hole. And this is the first such intermediate mass black hole detected by LIGO Virgo. In addition, you'll notice along the y-axis, there's a gap missing between this stellar mass systems and intermediate mass black holes. And in this region, which starts around 65 solar masses, this region is known as the pair instability mass gap. And what we find is that the primary component mass of GW190521 lies in this mass gap. And later in the talk, we'll hear from Michaela, who will discuss the importance of detecting a component mass inside of the pair instability mass gap. We can move to slide 8. Now, during the previous observing runs of LIGO Virgo, we did not have any detections of intermediate mass black holes. But still, we were able to map our sensitivity to intermediate mass black holes using simulation. So in the plot to the left, you can see our sensitivity to mass pairings of M1 and M2 in this IMBH mass regime. The sensitivity here is given in terms of our sensitive distance, which is just a measure of how far away we can see a given source on average. And what you notice here is that we are most sensitive in the mass regime right around GW190521, which is represented by the purple star. Now, also during previous runs, we were able to place an upper limit on the rate of intermediate mass black holes, and that number is 0.20 per gigaparsec cubed per year. And what we find with our latest results for GW190521-like events, we find the astrophysical rate to be 0.13 per gigaparsec cubed per year. And we find this to be consistent with our previous rate upper limit from 0102. Now I'll pass it off to Tito, who will discuss the statistical significance of this event.
Thank you, Brendan, and hello, everybody. In slide 9, I will give a little introduction to how we search for gravitational wave transients in O3, to then move on and discuss the significance of the new discovery. One of the ways we search for transients is called coherent wave burst, and is illustrated on the left part of the slide. This particular method is designed to detect generic transient signals regardless of their physical origin and their shape, and is based on wavelet decompositions of the data. Then we have 4 different searches called GST-LAL, MBTA, PyCVC, and SPEAR, which are designed to specifically detect signals from compact binary coalescences. And they can do this because we have very accurate models for these signals, which we can use to calculate the expected waveform and correlate it with the data to be very sensitive to these kind of signals. Let's go to slide 10, which discusses the initial discovery of GW190521. The signal was immediately found by 2 of these searches, coherent wave burst and PyCVC live, with false alarm rates of the order of 1 per 10 years. So this was sufficient to issue a public alert, and this is how the signal was initially discovered. Other pipelines found the signal with a higher false alarm rate, but all of these set of pipelines was nevertheless sufficient to do the initial discovery. 6 hours later, we issued an update to the sky localization of the event and to the estimate of the distance, placing it at about 4 gigaparsec using a simplified waveform model, which neglects some physical effects, which we will talk about later. And the signal was also classified as a likely binary black hole merger. Let's go to slide 11. Following the initial discovery, we spent some time to improve the calibration of the data and to investigate in detail the behavior of the instruments, which allowed us to clean the data and to remove data segments contaminated by times when the detectors were not behaving as designed. And this allows us to obtain a new set of data, which was searched again using some of the methods I described just a moment ago. And the result is on the table on this slide. So coherent wave burst produced a new significance for this event with a false alarm rate of about 1 per 5,000 years, which makes this event a very significant discovery. So this is a very confident detection of a gravitational wave transit. And GST-LAL and PyCBC also found the signal to be significant. And PyCBC, as will be shown later by the parameter estimation, had to deal with the fact that the signal was almost at the limit of the space covered by the search. And this is responsible for the relatively higher false alarm rate. And now I will give the word to Juan, which will tell you about the properties of this signal. Thank you.
Okay, thank you, Tito. Hello, everyone. So let's discuss now in more detail what we think are the properties of the source that generated GW190521. First of all, and as Tito and Brendan said, this is a particular, it shows a very weak pre-peak power. So given the shortness of this signal and the low frequency, we know already that this is going to be a very massive source. We can consider the standard scenario of a quasi-circular binary black hole merger, as we usually do, and we will show that the signal is consistent with this scenario. Under this assumption, the in-spiral portion of the signal is very short, quite weak, but nevertheless very informative, as we will discuss. The fact that the in-spiral is weak could also open the possibility to other alternative scenarios like eccentric binaries, even a head-on merger, or even a cosmic string cusp or kink. Michela will get into the discussion of these scenarios later. We will now focus on the vanilla scenario of a quasi-circular binary black hole without any eccentricity. So let's go to the next slide. We do this in a very similar way to the way that Tito described that CBC searchers do. We compare the incoming signal to an infinitely dense bank, in this case, of waveform templates for binary black holes. We have theoretical models, very accurate to compute these templates. And in this case, we're going to use three of these models. These are called NR surrogate, which is a model that is a surrogate for numerical relativity simulations. A so-called effective one-body model called SEOB, and a phenomenological model called IMR phenom. We also compared the data directly to numerical simulations of binary black holes. The PHM letters in the name of these models mean that these waveform models include higher order multiples, and also they account for orbital precession, which were neglected in the early warning that we gave 6 hours after the discovery of this event. I will highlight that all of these models lead to consistent source parameters. Our shorter discovery paper quotes results using the NR surrogate model, and those are the ones we will be quoting in this talk. And the longer properties and implications paper covers all the results at the time. So if we can go to the next slide, please. So first of all, let's look at the masses of the binary. In the left plot, you see the two-dimensional posterior distribution for the two masses, as well as the one-dimensional distributions for the two individual masses on the top and on the right. As you can see, the results are fairly consistent among waveform models, despite the difference in how they compute the waveforms. And the properties are the following. The total mass in the source frame is about 150 solar masses, which is Brendan heaviest compact binary merger ever observed by LIGO and Virgo. Despite the shortness of the signal, we constrain the mass ratio fairly well to be around 0.79. with a lower 90% limit of 0.5 or a mass ratio of 2, if you like the converse units. And the properties of the two colliding black holes are also very important. They show masses around 85 and 66 solar masses respectively. And the mass of the primary object, as Brendan described, is very interesting because it sits perfectly on the so-called pair instability supernova gap, which is a mass range in which we do not expect black holes to form from the stellar collapse of stars. Actually, the probability that the primary mass is out of this gap is only 0.32%. So if we can go to the next slide, then we get to discuss the spins of the black holes that collided to form our intermediate mass black hole. The spins, of course, have two properties: magnitude, which is bounded by 1 via cosmic censorship, and they have a relative orientation with respect to each other and also with respect to the orbital angular momentum. These properties have a huge impact in the dynamics of the orbit of the colliding object. These two properties are represented on the two disks on the left, which should be easier to interpret in the next slide. So this is my attempt to describe how this plot works. You can imagine the two black holes are in the centers of these two disks, and then the two arrows describe the magnitude as you move radially of these two spins, and the orientation of the spins describes the angle or the tilt with respect to the orbital angular momentum, which is represented by the vertical gray line. In the next slide, we can see the implications of what the orientations of these spins are. If the two spins are aligned or anti-aligned with the orbital angular momentum, then this leads to what we call a tilt equals 0. So we get a constant orbital plane and all the motion takes place in 2 dimensions. However, if we go to the next slide, we see that if we allow for random orientations of these two spins, then this makes the orbital plane precess. So it tilts up and down and creates the effect of orbital precession. And this has a huge effect in the waveform. So if we can go to the next slide, please. So now these are the properties we read for 190521. So first of all, there is support near the Kerr limit or the spin equals 1 limit for both spins, as well as there is support for 0 spins. So for this reason, we get a evidence for spins, but it's not an overwhelming evidence. When we compute the probability for having spinning black holes versus non-spinning black holes, we get 0.3 to 1 chances that these are spinning black holes. The magnitudes themselves of the spins, the ones we estimate, are around 0.69 and 0.73 respectively. And we also see support for highly misaligned spins, which is given by the fact that you see a lot of dark pixels near the equator of these two plots. When we compute the probability for precession versus non-precession, because note there is also support on the vertical directions of this plot, we get evidence for a precessing plane around 11 to 1, but it's not an overwhelming evidence once again. If we can go to the next slide, then we can discuss a very important property of this event, which is the distance and the inclination angle. And to discuss this, I want to introduce the concept of higher order multiples. Higher order multiples are the following. The gravitational wave emission from a binary consists on several gravitational wave modes that superpose on each other. When we look at the binary from face on, so in the direction that goes to the top of the binary or face off, the emission is completely dominated by what we call the quadruple emission mode, which is the one that goes as twice the orbital frequency. These face-on and face-on orientations are represented on the left, on the panel on the left, by the 0 and pi values, so the right and left limits of the plot. Signals emitted in this direction are also louder, so they can be seen from farther away. As you vary the orientation of the binary and you approach to its orbital plane, you start to see the whole collection of gravitational wave modes, but also the signal becomes weaker. And this orientation is represented in the panel on the left by it corresponds to the central vertical line at theta equals 1.5, or rather pi over 2. So why am I saying this? As Tito mentioned, we delivered a first estimate of the distance to this event 6 hours after the discovery. and we did not include the higher mode effect, or we get a distance of 4 gigaparsecs. Not using the higher modes means that it's very hard, higher modes to our analysis. Then we can distinguish better between these two cases, and we get a better constraint of the orientation. We place the source nearly face on or nearly face off, or rather we discard edge on orientations, and that makes the source to be farther. So our new distance estimate is around 5.3 gigaparsecs, plus minus 2.5 gigaparsecs approximately. And the inclination angle, as I said, is rather closer to face on or face off orientations, rather discarding edge on. We can search or we can compute the probability for having higher multiples in the signal. And we obtain a probability of 2.4 to 1 for not having those higher multiples on the signal, which is consistent with the orientation we infer. If you can go to the next slide. Now we can discuss the properties of the final black hole. So we have discussed the properties of the two colliding objects, and these form a final black hole. Once we know the properties of the binary, general relativity tells us or predicts what the final object should be. So we can compute these two values. So the plot on the left shows, again, the two-dimensional posterior distribution for the final mass and the final spin. And we infer the following values. First of all, the final mass is of around 142 solar masses. This differs by approximately 8 solar masses from the total mass, which means that eight suns have been converted to gravitational waves in the short stretch that this signal lasts for. And more importantly, there is no support at all below 100 solar masses, which makes this object the first conclusive observation of an intermediate mass black hole. The final spin we infer is around 0.72, which is interesting. That is consistent with remnants of non-spinning binaries, which again is consistent with the fact that the evidence we get for spins is not exactly overwhelming. So we can go to the next slide. So the fact that this signal is fairly dominated by the merger and ring down stages allows us to look at the strong field regime in a very nice way. A way to test the strong field regime, or to test general relativity on the strong field regime, is to check that we get the same final mass and spin estimates when we consider the full signal and when we try to measure these two quantities directly from the final object. So as I said before, one way we can compute the final parameters is to compute the parameters of the binary. Once we have this, general relativity tells us what the final object should be. And for this, we use the full information available in the signal. Now we have another way to measure the final mass and spin, which is shown in this slide. We look only at the portion of the signal that our waveform models tells us is being emitted by the final object, so to the late signal. Furthermore, if we look late enough in this so-called ring down signal, the signal is described as a damped sinusoid. So it's a signal with constant frequency that has a given damping time. This is very much similar to what happens when you hit a bell of a given shape. The frequency and the damping time are going to be given basically by the material and the size of this bell. Whereas in the case of the black hole, these two quantities are determined by the final mass and spin. This is what the no-hair theorem tells us if we ignore electrical charge. So measuring these two parameters, we infer the mass and the spin. Measuring the damping time and the frequency, we measure mass and spin. So we can see the two estimates in the next slide. And in the next slide, what we see is that the two estimates we get are consistent. So general relativity is passing this test. The blue contour represents our mass. So this is a redshifted mass. It's not the source frame mass I was showing before. And the final spin. So these are the two estimates according to our full waveform analysis. Whereas the gray contour corresponds to our estimate starting the ring down analysis only so after 12.7 milliseconds after the signal peak, so pretty late in the ring down. This is one of the reasons why the uncertainty is much larger. The other reason is that the ring down analysis does not impose any constraints on how this final black hole was formed, whereas the blue contour imposes that this black hole must come from a coalescing binary and restricts more the parameters. Both agree, general relativity passes the test. And now I will hand the floor to Michela, who will discuss the astrophysical implications.
Thank you, Juan. And good morning, good afternoon, or good evening, everyone, depending on your time zone. So we now discuss the astrophysical implications of this event. As we have already said many times, the final black hole, the random black hole of this event, is the most massive black hole ever detected with gravitational waves. And it is also the first evidence for a black hole in a mass range between 100 and 1,000 solar masses, not only from gravitational waves, but even considering electromagnetic data. This mass classifies it as an intermediate mass black hole. Intermediate mass black holes are the missing link between stellar mass black holes, like the one observed by LIGO and Virgo, and supermassive black holes that lie at the center of massive galaxies. And intermediate mass black holes could be the building block of supermassive black holes that could participate in the formation of supermassive black holes. But intermediate mass black holes are elusive objects. We are hunting for them with gravitational waves. We are hunting for them with electromagnetic data. And we have only a few strong intermediate mass black hole candidates from electromagnetic data. And all of the strong candidates have a mass in excess of 1,000 solar masses. And this makes our event even more unique. Moreover, observing this event, we have the proof that intermediate mass black holes can form via the assembly of smaller stellar-sized black holes. But the final black hole is not the only special black hole in this binary system. The primary component of the binary system that merged has a mass of about 85 solar masses, which lies in the peristability mass gap. Next slide, please. Massive stars undergo peristability when, at the end of carbon burning, they have a helium core mass above approximately 30 solar masses. At such large masses, pair production is effective in the stellar core. It softens the equation of state, reducing pressure, and the star faces an instability. For helium core masses between approximately 30 and 60 solar masses, this is a pulsational pair instability. The star undergoes pulsations, it loses a lot of mass, and then finds a new equilibrium. For bigger stars with helium core masses between 60 and 135 solar masses, approximately, we have a pair instability supernova, which completely destroys the star, leaving no compact object. The combination of pulsational pair instability and pair instability supernova is expected to open a gap in the mass spectrum of black holes between approximately 65 and 120 solar masses. The boundaries of this gap are uncertain. They are affected by large uncertainties because of the complex physics that is involved. In this plot, you see the masses of the binary black holes from O1 and O2, plus the masses of the black holes in this event. The red triangles are the final black hole masses. The black squares are the masses of the components. And the gray region represents the mass gap according to our current knowledge. And you see that even considering the very large uncertainties, the mass of the primary black hole in this event is right in the middle of the peristability mass gap. Next slide, please. So how can we form black holes with this kind of mass? Dynamics could help. And for dynamics here, I mean close encounters between black holes, close interactions between black holes and stars that happen in crowded environment like dense stellar clusters, here you see a globular clusters, and galactic nuclei. For example, in this environment, we could have hierarchical mergers, which means that black holes can form via multiple mergers in dense star clusters and galactic nuclei. And this process could produce black holes with mass in the periinstability gap. And we expect that binary black holes formed through hierarchical mergers have isotropically oriented spins, which is consistent with a large precessing spin. The main support for the hierarchical merger scenario is the observation of GW190521. We already observed a black hole with a mass in the periinstability mass gap that forms from the merger of two smaller black holes, and this is the final black hole of 170729, the most massive event that we observed in O2. In application papers, we have run a hierarchical Bayesian inference model to assess the possibility that 190521 is a second generation merger. Unfortunately, the results of our analysis strongly depend on the assumed properties of the first generation mergers. And this prevents us from drawing a strong conclusion about the hierarchical mergers. Next slide, please. Another promising dynamical scenario is the so-called stellar mergers in star clusters, especially young star clusters, like the one that you see here. If we merge a massive star with a helium core with another massive star that is still on the main sequence, this could lead to a very massive star with a helium core that is undersized with respect to the envelope. And if this core remains below the threshold for periinstability at the time of the stellar collapse, we can have the formation of a black hole in the periinstability mass gap. Of course, when it forms, the black hole is alone and lonely, but if it is in a denser star cluster, it can find a companion via dynamical exchanges, and this produces a binary black hole with a primary mass in the periinstability mass gap and with isotropically oriented spins. Next slide, please. And finally, we considered the Aegean disk scenario. Small black holes, stellar-sized black hole, can be trapped into an Aegean disk, and gas torques from this very dense disk favor the pairing of those black holes and hierarchical mergers, again, possibly leading to black holes with mass in a periinstability gap. This scenario has an intriguing feature. Unlike the other dynamical scenarios, it predicts an electromagnetic counterpart. And indeed, a candidate optical counterpart was recently reported associated with an Aegean. Unfortunately, the redshift of the Aegean is outside the 90% credible interval of the redshift measured for 190521 in our updated measurements. Next slide, please. So in summary, the possibility that this event can be explained with the isolated evolution of a massive binary star is hampered by the primary mass of this event, which is in the periinstability mass gap. However, this issue is somewhat softened by the uncertainties on stellar evolution, which leave open the possibility that the lower edge of the mass gap is higher than we think. On the other hand, all the dynamical scenarios that we have considered may produce binary black holes with mass in the gap and are consistent with large chi-p, but they are affected by large uncertainties on the rays and on the other properties of the black holes. So in the end, we can really say that GW190521 is a challenge, represents a challenge for current stellar evolution and dynamical models. Next slide, please. We have considered also some alternative scenarios. For example, the possibility that we are observing a head-on collision between two black holes, or the merger between primordial black holes, We consider core collapse supernovae and cosmic strings, but the data strongly favor BPH mergers over cosmic strings and core collapse supernovae. And finally, we consider the strong gravitational lensing hypothesis. The idea is that these two black holes could be smaller than we think, and we see them bigger just because there is a galaxy or a galaxy cluster between us, the observers, and the black holes, which has the role of a gravitational lens. We have analyzed this scenario in our implication paper, and we find no evidence in favor of strong lensing because of the low lensing rate, of the low optical depth, and of the absence of a multi-image counterpart. Okay, thank you very much. And now I give the floor to Alan for our conclusions.
Thank you very much, Michaela. So just to wrap up what we've learned here, gravitational wave GW190521 seems to be well described by waveforms derived from general relativity that incorporate spin orbital precession and higher order multipoles, but neglecting orbital eccentricity or any head-on collision or anything like that. The gravitational wave signal is consistent with a binary black hole merger source with a total mass of 150 solar masses at a luminosity distance of 5.3 gigaparsecs, a redshift of 0.8, corresponding to a look-back time of 7 gigayears when the universe was half the age that it is now. The remnant merged black hole is estimated to be around 142 solar masses in the intermediate mass black hole regime. And the more massive of the two black holes is estimated at 85 solar masses in the pair instability mass gap. It may itself be the result of a previous binary black hole merger in the hierarchical merger scenario. There's weak evidence of orbital precession due to in-plane component spins. There's a lack of evidence for higher order multipoles, and that favors a face-on orbit, a more distant source, and lower source masses. We see good agreement between the full in-spiral merger ring-down waveforms derived from numerical relativity and the ring-down only waveform. In fact, the amount of energy radiated in this signal is 8 solar masses, making it one of the loudest signals ever observed since the Big Bang. Forthcoming population paper will address whether 190521 is consistent with the mass distribution of black holes observed by LIGO Virgo up till now, which are all at lower masses. And we are asking ourselves the question of whether this more massive object fits into an overall generic population or it's a new population of binary black holes being observed for the first time. And let's see, how do I advance the slide when I'm talking? Okay, and so just to conclude, the future, of course, is loud. LIGO and Virgo, and now KAGRA, who's joining us for the 4th observing run, will have a large sample of 190521-like black holes. And that'll allow us to get a much deeper understanding of these objects. It is hard to see systems with even higher masses, but the next generation of ground-based and space-based detectors, such as LISA, will be able to detect intermediate mass black holes over a very broad range of masses. And that will serve to further deepen our understanding of binary black hole formation, of supermassive black hole formation, and the populations of these objects, as well as providing very powerful tests of general relativity. So that concludes our presentation. And I think now we can go to the question and answer period. And so if you will bear with me, I will try to find my controls well enough to go to the Q&A. I don't know if I can do this while still.
Alan, sorry to intervene. There are 2 panelists, Karan Jani and Max Easy, who would like to be promoted. Can you promote them yourself or should I?
Give me a second to do that. Pardon me, everybody. So we've got Karan. Wow, there's 500 people, so it's kind of hard to find the right person. But
find them up. You find them with a search above.
Oh yeah. So Karan is going to be promoted to panelist, and Max is promoted to panelist. All right, I am now looking at our Q&A. I see that there haven't been any upvotes. You know, you're allowed to upvote if you're on Zoom. And I have not seen any. I do not see the upvotes here. So maybe because there aren't any. Somebody try upvoting. Let's just see if we can do it.
No, when we started it, we forgot. Sorry, we forgot to turn it on, and now I think it's a little bit dangerous to do it. So
fair enough. I do see that many of the questions were answered in real time.
I think we can.
All right. So we'll go through the questions in some order, and let's just start with the very first one from Zhelong Li. Can the discovery of such a massive set of black holes modify the existing black hole theory? Do we have a panelist who wants to answer that question or address that question? Panelists, you have to raise your hands so I can call on you. And otherwise, I will do my best here. We don't need to modify existing black hole theory. So far, this observation has not demanded anything beyond general relativity as the description of black holes, of black hole binaries, and of black hole binary mergers, which is a very non-trivial statement. Michaela.
Yeah, but if I may chime in, from the astrophysical point of view, this event will certainly push us and push the theorists who do research on the astrophysics of black holes to push their models, to revise their models, to explain the formation, especially of the primary mass of this event and the formation of these binaries. So from the astrophysical point of view, definitely the mass of the primary and the existence of this event are kind of a paradigm shift. And you will see, I guess you will see a lot of new work on this in the next few months.
Thanks very much, Michaela. Let's see, from Howery we get, can the lack of a large kick be due to the closeness of a supermassive black hole, e.g. merged black holes that are in the center cluster of a galaxy? Michaela, do you want to answer that one, or do you want to lower your hand? Karan is raising his hand. Go ahead, Karan.
Yeah, hi. So regarding the kick, the inferences that we have so far, fairly broad. This is the best constraints we could have. The spins, the kick would directly impact with the spins. It's not showing any presence because of an external object that the kick would have suppressed. This is just internal to the two mergers. And yet again, this could be fairly broad. It could be greater than few 100 to 1,000 kilometers per second. It's consistent. So we don't really see any suppression due to supermassive black hole.
Thank you, Karan. I'm trying to juggle my screen. Can you explain the rate of events associated with this event? How can you explain it?
I can answer that.
Please go ahead, Sergey.
Yes. What we do here is that we have, of course, simulated signals. We do parameter estimation with simulated signals, and we know the parameters of this event. So we can simulate a lot of signals with which are similar to GW190521, and then make it distributed uniformly in space Then we take this sample and inject it into our data, detect with our pipelines, and it gives us how often we can detect signals like GW190521. And from here, knowing what kind of search volume we observe, we can infer the typical rates for these events. We can find how often they happen per unit of space and per time, unit of time.
And it should be noted that although there are numerous predictions for what these rates should be in the literature, it's all speculative. And measuring this rate helps us to narrow the range of astrophysical scenarios that produce intermediate mass black holes, and thereby help us understand better what's really happening astrophysically. So it's not, the rate that we measure is not by any means way out of line with previous predictions. It helps us narrow those predictions. All right, here's a question from Fabio. What does it mean that the mass range, that in this mass range black holes should not exist? Should we revise astrophysical models and or gravity theory? Which is the best candidate in astrophysics and gravity theory? Michaela, do you want to take this?
Yeah, I think it's quite similar to the previous question. So from the side of astrophysics, we definitely have several things to study and to improve in our models, starting from understanding better the boundaries of pair instability. I think the pair instability mass gap has large uncertainties, as I said, and this is a key point to address as soon as possible. The dynamical scenarios that I presented during my talk are very interesting ones, and all of them kind of very new. They were proposed maybe in the early years of the, at about 2000, 2002, but they are still in a condition where a lot of improvements is possible. So definitely, I think from the astrophysics point of view, there is a lot to do, a lot of work to do, and this makes it very exciting.
Thanks very much. Next question is from George Smoot. The chance of strong gravitational lensing is roughly 10 to the minus 3 or less for a randomly chosen event. What is the probability for one selected to be a very large signal and to have a primary mass of 85 solar masses? Clearly much higher. Johnny.
Yeah, hey, hello, I hope you can hear me.
Yes.
The actual answer, of course, depends heavily on the black hole mass distribution that one expects. So it's not very clear how you can directly answer this, but as we write in our paper, if we do assume that there's some maximum mass for around 50 or 60 solar mass, then the lensing optical depth, so the chance of lensing, is around 10 to the minus 4.
Very good. Thanks very much. Next is Jervin. With regard to the astrophysical implications of the observation, I think it's been established that this is indeed a step further into exploring black holes. My question is, would tuning current instruments or establishing new ones, specifically attuned for bigger black holes, help in detecting black holes in this region? Any takers amongst the panelists? If not, this is an easy one. The answer, of course, is yes. And in particular, as Brendan explained, the higher mass systems merge at lower frequencies. You can see that LIGO and Virgo currently are limited. They have very little sensitivity below, say, 20 hertz. Next generation ground-based detectors are going to push in the direction of just a few hertz of sensitivity down to a few hertz. In other words, opening up quite higher mass regime for very higher mass mergers. But in addition, LISA will operate at much lower frequencies, millihertz to hertz type frequencies, where intermediate mass black hole mergers and supermassive black hole mergers, well, starting from as low as thousands of solar masses on up, will become immediately observable. And so in the coming decade or two, there will be far better instrumentation for detecting these much higher mass systems, and even potentially allow us to fill the gap that Michele referred to between solar mass black holes, stellar mass black holes, and supermassive black holes. And that leads naturally to Selma's question: would we see events like this ahead of time with LISA in the future? Karan.
So quick thing is that we would see this population, and it would be a multi-band population. So at least 4 to 10 years before the merger, we would start seeing the signal. But just to clarify, for the specific signal, this is fairly far even for LISA's horizon. What we can infer is from the number of events that the rates we have, we may see a couple of handful of dozen or so such source, but not, of course, not something as far as GW190521 with the SNR that would be required.
Right, and Karan is talking about seeing it with LISA days, weeks, months, years before it's seen in ground-based detectors at higher frequencies. But that is something that's being explored by many people. It's a very exciting prospect, and we should look forward to it. Next question is from Matthew. Is it correct to say that the 1G plus 1G first generation versus 1G plus 2G and 2G plus 2G inference would be significantly different for a nuclear star cluster or an Aegean? Given the environment is unknown and could in principle be a field event, does that mean that this inference has meaning only within one specific assumed scenario? Chase, would you like to give that a try?
Hi, yeah, can you hear me?
Yes.
So yes, the inference would change if you assume a different cluster environment. We did do an order of magnitude check by increasing the cluster mass to something Aegean-like, and found that the odds ratios actually do increase by a few orders of magnitude. So the inference is sensitive absolutely to the environment that you assume.
Very good. And a related question from Leo that probably has had some discussion already in chat. Leo wants to know if the model selection is prior dominated, or if there really is any discriminating power in the data. Maybe a different way to ask is, if we use the event to infer posterior on the relative rates of 1G plus 1G versus 1G plus 2G or 2G plus 2G events, what is the entropy of the posterior relative to the prior on these rates?
Yeah, so the, sorry, if you don't mind, I take this. So there's no prior directly on the rates themselves. The prior is on the mass and spin distributions of the 1G population, because we calculate the relative rates of 1G, 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 2G, and 2G, 2G mergers as a function of the fraction of retained merger products, which is itself a function of the 1G, 1G mass and spin distributions. So I don't have a clear answer on what the entropy is relative to the priors, but this is something to look into.
Great. Next question. What kind of electromagnetic, from Sarah, what kind of electromagnetic counterpart do we expect from the Aegean scenario? Okay, we should have had Imre here. So if you read the papers by Graham and by Bartos and others, you will see that you can expect to see a flare, and indeed they believe they do see a flare in the optical from such an Aegean, sort of shorter in duration than a typical Aegean flare. And the Aegean that they've identified as having a flare at around the same time is at about is at a redshift of 0.43 or 0.44, something like that. So the candidate that they observe, there's quite a large amount of uncertainty depending upon the material, the density of material and other factors in the Aegean disk. But what they find, they can claim to be consistent with expectations for a merger like this in an Aegean disk. That's probably not an adequate answer, but it's the best I can do right now. Okay, Jose asks if you spoke at the end of the presentation about the possibility of these binary black holes being of primordial origin. What would you say would be the best way of ruling out or confirming this possibility? Nelson?
Yeah, I'll take that. So I think it'd be difficult to rule in or rule this out in the near future, but we should mention that LIGO and Virgo do have searches for compact binary in-spiral signals where we're looking for component masses to be less than 1 solar mass. And if you found a signal where one of the component masses or both were below 1 solar mass, you'd be hard pressed to explain it as a neutron star. And as a black hole, the logic goes that the only probable way to form it, or most probable, is primordial. So I think the search for compact objects below 1 solar mass would be strong evidence for primordial black holes.
Yeah, another possibility for next generation detectors is to identify sources at redshifts greater than 20 before the first stars, when primordial black holes may have already existed and already have formed binaries and already be merging. It's hard to detect such things; they're very distant, but one can hope for such things in next generation detectors. Maurice asks, given its estimated event rate, n = 1, is the binary mass consistent with the extrapolated tail of the mass distribution of the existing observed sample? Tom, you want to take that one?
Sure. So in the paper, we did analysis looking at the 10 previously observed events in 01 and 02, and then we showed that if we take the population that we deduced from those events, which has like a cutoff at the top end of maybe 45, 50 solar masses, this detection is clearly outside that. Okay, I seem to have some background noise. Let's hope it doesn't continue too bad. Okay, but we've since detected in 03 several dozen more binary black hole events, and I think we'll be able to better answer this question when we do a kind of combined analysis, because we have now a much bigger sample of possible binary black hole masses. So I guess the answer is really stay tuned. Hopefully in the next few weeks, you'll get a much more quantitative answer to this question. As people are working on this question basically almost as we speak, and the results are almost ready to be packaged up and published. So watch this space.
Great. Fabio has a follow-up question. Are there time limits in dynamical models given the estimated age of the universe? Does it allow to rule out some multi-generation mergers? Michela.
Indeed, I agree with Fabio that this is a cool problem, a cool subject. More than time issue, I would say that the key point here is the escape velocity. So basically the mass of the star clusters, because at the merger, the two black holes usually receive a relativistic kick, and this kick can be of hundreds of kilometers per second. So we can basically already say that the smaller clusters like open clusters and youngster clusters of small size are not really efficient in producing these mergers, because these hierarchical mergers, because the black hole remnant, the final black hole, is ejected from the cluster. While in more massive clusters, for sure in nuclear star clusters, it is much easier to retain the black holes. And so yes, in this case, we could be limited by the lifetime of the nuclear star cluster.
Okay, thank you. Fortunately, Barry McKernan is on and is giving a more authoritative answer to Sarah's question than I could have, so let me read it. The electromagnetic signal in an Aegean is two parts. Initially bound gas around the binary collides with disk gas. And this is relatively low luminosity and is hard to detect. The second part is a Bondi accretion process. High rate of accretion and greater likelihood of seeing it, and the black hole is kicked out of the dense disk midplane into the thinner disk atmosphere. I'll add that in their model, because of that kick, it's still bound to the supermassive black hole in the center of the Aegean, and so it will orbit and re-enter the disk in some later time. That's actually predicted in the data, in their paper. So we can go and look during that time. They will, and hopefully see something. But Barry hastens to say that they have a lot of work to do on the model details. Thanks very much, Barry. I needed that. Let me go on, unless I'm being told by somebody, am I, that we're out of time. I'm going to keep on going. Until I'm told, let's end it. So, but please, let's stop the Q&A so that it does end eventually. So Andrea asks, with the improving sensitivity of LVK in the next runs, I would expect an increase in this kind of black hole binaries with primary masses in the mass gap. I guess this would be important for the current merging scenarios and possibly answer how common are these events. Is this correct? Tyson, you want to take that?
Yeah, yes, it is correct. So it's hard to understand a population when you look at just a single individual, but we're doing the best we can. But as ground-based detectors improve, and furthermore, as space-based detectors come online, then we should be able to sample many more members of this part of the population and understand these different scenarios better. So you hit the nail on the head.
Great. This is our last question, so we'll end. From Gangwan, although you say the remnant is an intermediate mass black hole, what is the minimum mass of astronomically observed candidates and observations?
I think I can take this.
Thanks, Michaela.
Okay, so I think the smallest one among the very, very strong candidate intermediate mass black holes is HLX1 in a galaxy at about 100 and something megaparsec from us. It is observed because it's really high X-ray luminosity and modulation of the X-ray luminosity, and it is associated with a radio jet. So putting together all the constraints that come from the high X-ray luminosity, the optical counterpart, there is also an optical counterpart, which I forgot to mention, and the radio jets, we have an estimate of the mass that is between 9,000 and 90,000 solar masses. It could be lower because the accretion process is really uncertain and the distance of this object is quite uncertain too. But I would say that the strongest electromagnetic candidate with mass significantly below 10 to the 5 solar masses is HLX1, and the estimate of the masses suggests a black hole with a mass of 10,000 solar masses or so. I can point you at some references if you're interested.
Thanks very much, Michaela. I believe that we are at the end of our presentation now, and I thank everyone for your participation, for your interest. On behalf of the LIGO Scientific Collaboration and the Virgo Collaboration, we very much appreciate your interest in our work, and we look forward to all the papers that you are going to write on this subject. Let's see, is there anything else we need to do before we close? If not, thank you all again and enjoy the rest of your day and week.
Thank you.
Bye.
Bye-bye.